Welcome, cosmic explorers. Imagine for a moment that you're standing under a clear night sky. As you gaze up at the twinkling stars and swirling galaxies, you might feel a sense of awe and a flood of questions. Well, you're not alone. Today, we're diving into the 15 biggest unanswered questions in astronomy. Imagine you're at a cosmic party. You can see the guests, hear the music, smell the food. But then you realize that 85% of the party is invisible, silent, and odorless. Welcome to the dark matter conundrum. Dark matter is like the universe's invisible scaffolding. We can't see or touch it, but we know it's there because of its gravitational effects on visible matter. It's what keeps galaxies from flying apart and helps shape the cosmic web of the universe. But what exactly is it? Is it made of exotic particles we haven't discovered yet? Or is it a sign that our understanding of gravity needs a major overhaul? Scientists have been hunting for dark matter particles for decades, but so far, this cosmic hide-and-seek champion remains elusive. If dark matter wasn't puzzling enough, meet its even more mysterious cousin, dark energy. Imagine you're blowing up a balloon, but instead of getting harder to blow as it expands, it gets easier and easier, inflating faster and faster on its own. That's basically what dark energy is doing to our universe. It's the name we give to the unknown force that's causing the expansion of the universe to accelerate. This discovery, made in the late 1990s, threw a cosmic wrench into our understanding of physics. Is dark energy a property of space itself? A new field that permeates the universe? Or is it a sign that Einstein's theory of gravity needs a 21st century upgrade? Right now, we simply don't know. But this invisible force makes up about 68% of the universe's content. So figuring it out is kind of a big deal. All right, let's wind the cosmic clock back to the beginning. The Big Bang Theory explains how our universe expanded from a hot, dense state about 13.8 billion years ago. But here's the mind bender. What happened before that? This question is so tricky that some physicists argue it might not even be meaningful to ask what came before the Big Bang, since time itself might have started with this event. Others propose ideas like a cyclical universe that expands and contracts eternally, or a multiverse where our Big Bang was just one of many. Some theories even suggest that the Big Bang emerged from a kind of quantum fluctuation in a pre-existing state. But the truth is, we're still in the dark about the ultimate origin story of our cosmos. It's like trying to read the pages of a book that come before page 1. Now for the question that's likely crossed everyone's mind while stargazing. Are we alone? With billions of galaxies, each containing billions of stars, and potentially trillions of planets in our observable universe, it seems unlikely that life only evolved on our pale blue dot. But if life is out there, where is everyone? This puzzle, known as the Fermi paradox, has stumped scientists for decades. Are we looking in the wrong places? Are we misunderstanding what alien life might look like? Or are we truly alone in this vast cosmic ocean? From scanning the skies for radio signals to searching for biosignatures in exoplanet atmospheres, astronomers are leaving no stone unturned in the quest to answer this profound question. The day we detect signs of extraterrestrial life, whether it's microbial or an advanced civilization, will undoubtedly be one of the most significant in human history. Black holes, cosmic vacuum cleaners so powerful that not even light can escape their grasp. We've imaged their shadows and detected their gravitational waves. But what lies beyond the point of no return? The event horizon? According to Einstein's equations, at the center of a black hole lies a singularity, a point of infinite density where the laws of physics break down. But many scientists are uncomfortable with the idea of infinities in nature. Could there be something else inside? A portal to another universe? A core of exotic matter? Some theories suggest that information that falls into a black hole might be preserved on its event horizon, like a cosmic hologram. Others propose that black holes eventually evaporate through a process called Hawking radiation. But until we figure out how to reconcile quantum mechanics with gravity, the interior of black holes remains one of the most perplexing puzzles in the cosmos. Imagine the universe as a cosmic boxing match between matter and antimatter. According to our best theories, equal amounts of matter and antimatter should have been created in the Big Bang. But here's the twist. When matter and antimatter meet, they annihilate each other in a burst of energy. So why is there anything left? Why is the universe we see made of matter, with hardly any antimatter in sight? This cosmic imbalance, called matter-antimatter asymmetry, is crucial for our existence, but we don't know what caused it. Did some unknown process in the early universe create slightly more matter than antimatter? Or are there vast regions of the universe made of antimatter that we just haven't found yet? Solving this mystery could reveal fundamental truths about the nature of the universe and why we're here to ponder it. At the heart of nearly every large galaxy lurks a supermassive black hole, millions or billions of times more massive than our sun. But here's the cosmic chicken and egg problem. Which came first, the galaxy or the black hole? These cosmic titans pose a problem for our current theories. They're so massive that they couldn't have formed from collapsing stars like smaller black holes. And some of them appear to have been around when the universe was less than a billion years old, barely a cosmic toddler. Did they grow from smaller seed black holes that somehow grew incredibly quickly? Did they form directly from the collapse of enormous gas clouds in the early universe? Or is there some other mechanism we haven't thought of yet? Understanding how these cosmic behemoths came to be is crucial for unraveling the evolution of galaxies and the structure of our universe. Imagine you're a radio astronomer, quietly listening to the cosmos. Suddenly, your instruments light up with an incredibly bright burst of radio waves. It lasts for just a millisecond, and then it's gone. Welcome to the puzzle of fast radio bursts, or FRBs. First discovered in 2007, these cosmic flashes pack a huge amount of energy into a very short time. Some of them even repeat, but with no apparent pattern. They've been detected coming from all over the sky, some from within our galaxy, others from billions of light years away. Are they the death cries of neutron stars collapsing into black holes? The exhaust beams of alien spacecraft? Or something we haven't even imagined yet? While we've made progress in tracing their origins, the exact mechanism behind these cosmic lighthouses remains a tantalizing mystery. Just when we thought we had our cosmic neighborhood figured out, the outer solar system throws us a curveball. In 2016, astronomers noticed something odd. Several distant objects in the Kuiper Belt seemed to be following unusual orbits, as if they were being shepherded by the gravity of an unseen planet. This hypothetical world, dubbed Planet 9, would be about 5 to 10 times the mass of Earth and orbit the Sun every 10,000 to 20,000 years. But if it's out there, why haven't we seen it yet? Well, it would be incredibly faint and moving very slowly against the background stars. The hunt for Planet 9 continues, with astronomers scanning the skies and citizen scientists combing through data. Whether we find it or not, this search is pushing us to better understand the outer reaches of our solar system. Who knows what other surprises might be lurking in the cosmic darkness? Imagine the early universe, a vast, dark expanse of hydrogen and helium gas. Then, suddenly, light appears. But how do we go from cosmic dark ages to the brilliant starscape we see today? The first stars, known as population 3 stars, are thought to have been monsters perhaps hundreds of times more massive than our Sun. They would have lived fast and died young, exploding as supernovae and seeding the universe with heavier elements. But we've never actually seen these cosmic pioneers. They formed when the universe was less than 100 million years old and burned out long ago. With next-generation telescopes like the James Webb, we're hoping to peer far enough back in time to catch a glimpse of their explosive deaths. Understanding these first stars is crucial to unraveling how the universe evolved from its simple beginnings to the complex cosmos we see today. Let's fast forward, way forward. What's the ultimate destiny of our universe? Will it expand forever, growing colder and darker? Will it eventually stop expanding and collapse back on itself in a big crunch? Or will dark energy tear apart the very fabric of space-time in a big rip? The answer depends on a cosmic tug-of-war between gravity, which pulls things together, and dark energy, which pushes things apart. Right now, dark energy seems to be winning, causing the universe's expansion to accelerate. But will this always be the case? Some theories even suggest a cyclical universe, endlessly expanding and contracting. Others propose that our universe might be a bubble in a vast multiverse. The truth is, predicting the fate of the universe requires understanding dark energy. And as we've seen, that's still a big question mark. Galaxies are the grand cities of the cosmos, home to billions of stars, vast clouds of gas and dust, and usually a supermassive black hole at the center. But how do these cosmic metropolises form and change over time? We've observed galaxies in various stages of evolution, from the earliest formations in the distant universe to our mature Milky Way. But many questions remain. How do galaxies acquire and retain their gas, the fuel for star formation? What role do galactic mergers play in shaping a galaxy's destiny? And how do galaxies and their central black holes influence each other's growth? One of the biggest puzzles is galactic archaeology, piecing together the Milky Way's history from the motions and compositions of its stars. It's like trying to reconstruct the entire history of a city by studying its current inhabitants. Challenging? Absolutely. But it's giving us unprecedented insights into our galactic home. Time. It marches relentlessly forward in our everyday experience. But in the realm of physics, it's not so simple. Einstein showed us that time is relative, flowing differently depending on gravity and motion. But many deeper questions remain. Is time a fundamental property of the universe? Or does it emerge from more basic phenomena? Why does time seem to flow in only one direction, the arrow of time, when most physical laws work equally well forwards and backwards? And how does time behave in extreme conditions, like inside a black hole or at the moment of the Big Bang? Some theories even suggest that time is an illusion, and that past, present, and future all exist simultaneously in a block universe. Understanding the true nature of time could revolutionize our understanding of everything from the origin of the universe to the nature of consciousness. Prepare for a mind-bending possibility. Our universe might not be the only one. The idea of a multiverse, a collection of parallel universes, has moved from the realm of science fiction to serious scientific consideration. Several theories in modern physics point to this possibility. Inflationary theory suggests our universe might be one of many bubble universes constantly forming in a rapidly expanding cosmos. String theory proposes an enormous number of possible universes with different physical laws. And the many-worlds interpretation of quantum mechanics suggests that every quantum event creates a branching of reality into multiple universes. But here's the catch. How can we test these ideas? By definition, other universes would be outside our observable reality. Finding evidence for or against the multiverse is one of the greatest challenges in modern cosmology, pushing the boundaries of what we consider science. Our final question brings us closer to home, yet it's no less profound. How did life arise on Earth? We know life has existed here for at least 3.5 billion years, but its origins remain shrouded in mystery. Did life start in warm little ponds, as Darwin suggested, in deep-sea hydrothermal vents? Or did it arrive from space, hitching a ride on comets or meteorites? And what were the key steps from simple organic molecules to self-replicating systems that could evolve? This question bridges astronomy, chemistry, geology, and biology. Understanding life's origins on Earth is crucial not just for completing our planet's history, but also for guiding our search for life elsewhere in the universe. It forces us to grapple with the very definition of life and our place in the cosmos. And there you have it, Cosmic Explorers, 15 of the biggest unanswered questions in astronomy. From the nature of dark matter to the origin of life. These mysteries remind us of how much we have yet to learn about our universe. But far from being discouraging, these questions are what drive science forward. They inspire new theories, new experiments, and new ways of looking at the cosmos. And who knows? The key to unlocking one of these mysteries might be in the mind of someone watching this very video. Remember, every great discovery in science started with a question, with someone looking at the world or the stars and wondering why or how. So keep questioning, keep wondering, and keep looking up at the night sky with awe and curiosity. Which of these cosmic mysteries intrigues you the most? Share your thoughts in the comments below. And if you enjoyed this journey through the universe's biggest questions, don't forget to like this video and subscribe to our channel for more cosmic content. Until next time, keep exploring the wonder of our universe.